Okay, so good evening everyone. So I welcome you all to this week 9 live session on the course Deep Learning. This course is provided by Professor Prabir Kumar Biswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. So in this particular live session, we'll start by solving the week 7 quiz. Followed by that, we'll solve week 8 quiz as well. And then we'll do a hands-on session on implementation of VGG16 and ResNet, and specifically we'll be implementing ResNet 18. So there are several versions of ResNets are there. So ResNet 18, ResNet 50, ResNet 34, 101. So in this particular live session, we'll be using ResNet 18 only. So we'll be using TensorFlow and Keras-based distribution to implement these neural network models. And along with that, we'll be using MES dataset again to classify the images into 10 different categories, that is from 0 to 9. So let's dive into the uh, quiz part first. So I will start with week 7 quiz, and then followed by that, we'll solve the week 8 quiz. And another thing is that there are 2 TAs in this particular course. So if after completing the week 7, week 8 quiz, and then that Python implementation, if time exceeds, then there is another TA is there. He can take some questions, some practice questions for week 9 quiz as well. So let us start solving the first. Let us start solving the first question. So the first question states that what is the main advantage of layer by layer pre-training of deep autoencoder? So we have seen that there is a special class of autoencoder is there that is called a stacked autoencoder. Stacked autoencoder. So stacked autoencoder is basically a deep autoencoder. So there you have multiple numbers of it. This one is an input layer. So after the input layer, you have multiple number of encoder layers, which basically encodes the input data to a latent space. So let it be the latent space, and followed by that, you have the subsequent decoder layers to decode back the information. And this is the output layer of the autoencoder. So this is the output layer of autoencoder. Now, to train these sort of autoencoders, what we basically do is we do a layer by layer pre-training. What basically means is that, for example, if this is a layer number 1 or encoder 1 layer, first encoder layer. So what we'll do, we'll basically train this first layer as a single one, and this would be, let's say, the decoder. This is the output layer. So you have a shallow network. So will you give an X over here? This is the latent space, and then after that you will decode it back. So it will give you an X hat. Then you will have a loss function. It is basically MAC of X comma X hat, and that loss function will minimize. So arg min of L, which is basically, if I write in terms of X and X hat, so loss of X and X hat, and these are the weights and biases that has to be optimized. So this is the weight of the encoder, so WE, and this is the bias, this is the weight of the decoder part. And let me consider that you have absorbed the bias term inside the weight. So we have seen from SVM lecture and all that how if you have given an equation like this, for example, y equals to wx plus b, we know that how to absorb the bias term inside the weight term using the concept of matrix factorization. For example, if you have weights like this, w1, w2, dot 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 wn, and you have x1, x2, dot dot xn, and you have a bias term over here, B. So what you can do, you append 1 over here, and then you can put a B over there. For example, W1, W2, Wn, followed by B, and then you can write x1, x2, xn, and then 1. So this will give you that Wx plus B thing. Now, I'm considering that We and Wb, they basically you have already absorbed the weight bias terms inside these two factors. So arg mean We, comma Wd. So these two have to be optimized by minimizing this particular loss function, which basically refers to the MSE between input and output. Now, if you train this particular layer, after that you have to train the second layer, that is E2. Now, when you train E2, you have an input layer, followed by that E1 already you have pre-trained, then you have E2 over here, and then subsequently you'll have the decoder layers, and this is the output again. Again, you will train, already you have trained E1, now you'll train with E2. Considering that whatever weights you have given over here, they basically comes from the previous training. Now, in this way, you train this whole encoder part, and subsequently, as you know that encoder and decoder have to be simultaneously trained. So encoder decoder layer by layer training will be done subsequently. So this is basically called the layer-wise pre-training of an stacked autoencoder. Now we have to scan through what is the main advantage basically. So let me just give you a glimpse. For example, if you train these layers initially, so all these layers are trained, let's say. All these layers are initially trained. So you know that what is the initial estimate of the weights for these particular layers. So you know the We, let's say all, Wd all. So already you know that what is the first initialization of all these weights, because already you have pre-trained those models. So you will just use those particular weight values. So W1, W2, W3, W4 as the first initialization of this particular of this whole model. So these pre-trained weights you can use as the first initialize weight values rather than initializing them using a rand function. What happens is that if you let's say you have not pre-trained the model, so what you will do, from scratch you have to train this whole big model. So initially we know that using for example, all these deep learning models are optimized using the gradient descent optimization technique. So in case of gradient descent optimization technique, what is the formula? So that is W of n plus 1 is basically W of n minus eta into grad of the loss. So let's say grad of error with respect to the weight values. Now, this Wn at the first iteration, whatever W at the first iteration, it will be W of 0. Now, this W of 0 will be initialized using a rand function. Now, what will happen is that if you use a rand function, now your model will take substantial amount of time to convert. However, already you can see that while these layers have been pre-trained, already you have done a loss minimization. So that means you already have got some good weights by which you can initialize this whole model, which will effectively converge this whole loss minimization process quite faster. So the main advantage of this particular layer by layer pre-training is basically you have a sort of good initialized weights, which will basically help you in converging the whole problem in an easier manner. Rather than if you train the whole model at once, it will take substantial amount of time to converge. And the weights that you initialize at random, those are not a good good weights that has to be initialized. So for this particular question, so in case of option B, we can see that it provides better initial weight values. So that is what we are telling, that as you are pre-training the model, so you already have done some optimization on these particular weights, and you have optimized this curve in a substantial manner so that your weight values are quite good. Now you can use those weights while training the whole model again. So these weights basically are sort of good weights that has to be initialized while training this whole model, rather than training them from scratch by using a rand function. So it provides better initial weight values for the entire network. So this one is true. It allows parallel training. So it does not allow parallel training. So that is also if you see the current papers, let's say 23, 24, 22 onward, now some papers are coming which basically support states that you can parallelly train this model. But the thing is that we need to consider the base paper. So where in the base paper, because this is a coursework, we are not doing extensive research based on the papers that are coming now and then. So we need to consider that the base paper, when those things basically came up, so at that time we didn't have the words of parallel training of this different hidden layers. So option C is incorrect. Then option D is, it guarantees perfect reconstruction of the input data with minimal error. You cannot actually guarantee that by any sort of training. You cannot guarantee that whatever you train by, or by which manner you train, you will get perfect reconstruction error. That is basically dependent on how difficult or how easy your problem is, by which you can reconstruct the input data in an efficient manner. For that, you need to sometimes you need to change the loss function as well. For example, in some cases maybe MSE cannot be used, some other loss function can be used, so that you cannot just ensure that your reconstruction loss will be very much minimal by just using a layer wise pre-training. That is not possible. So option D is also wrong. Then option A is, it reduces total number of weights and simplifies the optimization process. It might simplify the optimization process because you have got the weight values pre-trained, but it cannot reduce the total number of weights. So you can see that whatever weight values over here, that you are using over there as well. So it is the same number of weights that you are using when you are pre-training the model, and when you are again retuning or fine-tuning this whole model. So anyway, you are not able to reduce the weight. So that is why the reduce of total number of weights, that is incorrect. So therefore, option A is also incorrect. So you can see that option B is the correct answer for this particular question. Any query for this one? Okay, I hope there is no query. Okay, the second question states that uh, select the correct option. Yes.
In our own words. Okay, that's easy. That's a good way to get started. I know exactly how.
The second one states that you have a denoising autoencoder, and we need to find that which one is the correct option. So statement A is, the loss is between original input and reconstruction from a noisy version of the input. Yes, that is true, because if I just show you the schematic of the denoising autoencoder over here, so again you have a latent space over here. Let me consider I am using an undercomplete autoencoder structure, which basically reduces the dimensionality in the latent space, and then again reconstruct back. Now, you have an input, let's say you have input X. What you do is basically to perturb this particular input with a noise, let's say eta, and you produce a noisy version, that is, let's say X noisy. Now you feed this particular X noisy in the input, X noisy in the input, and at the output you basically try to get you try to reconstruct back an output that is X hat, and you try to minimize the MSE between the reconstructed output and the origin. So this one is a clean signal. This one is noisy one. So this is noisy, and you feed this particular noisy signal over here in the input. At the latent space, it encodes something. So at this particular point, you get the latent space, which basically extract some hidden features or representations from the input noisy data, and then these particular features or these particular representations are used by the decoder to decode it back and to generate a denoised version of the noisy input. So this is the denoised output. And now as we are arguing that the output is a denoised one, so we need to have a measure by which we can understand or quantify that what sort of denoising we have obtained. So to obtain that particular quantification, what we do is basically we take a MSE between the clean version and the denoised version. So this is the loss function of the denoising autoencoder. So statement A is loss is between the original input. So this is the original input and reconstruction from a noisy version. So this X hat is basically reconstruction from a noisy version. So we fed this noisy input, and at the output we get a reconstruction X hat, which is basically coming from the noisy input. So the loss function is MSE between X and X hat. So option A, statement A, is true. And the second statement that it provides this, or statement B, is denoising autoencoder can be used as a tool for feature extraction. So we can see that while doing the encoding operation, so over here, if this is the encoder part and this is the decoder part, we can see that the autoencoder model at the latent space tries to extract some hidden features or representations from the input noisy data. So these are basically the features extracted at the bottleneck or the latent space. So therefore, denoising autoencoder can be used as a tool for feature extraction, as the latent space basically extracts some hidden representation or feature from the input data. So statement B is also correct one. So for this particular case, we can see that option D is both the statements are true. This is the correct option. Okay, so the third question basically asks that which of the following is a linear operator? So any linear operator, or we have seen that the linear operators, they basically follow superposition theorem. Superposition theorem, or the response or the transfer function. If I talk in terms of mathematically, the transfer function y given x, the response should be linear So this is not a line. So the response should be linear and the line should pass through the origin only. So in the last class, we have seen that y equal to mx. This is a linear system or a linear operation is happening over here, linear system. However, y equal to mx plus 3, even though the response is a line only, but as far as system is being concerned or operation is being concerned, as this particular system does not obey the superposition theorem, so this particular operation or the system, as far as the system is concerned, so this is not a linear system. So non-linear system. For example, if I talk about electrical engineering, you have seen that we write that V equal to IR. If you draw it, you will see the responses passing through straight line. Then for inductance also phi equals to Li, and for capacitance also Q equal to CV. All these particular relations are linear relations. However, if I talk about, let's say, a piecewise constant diode model. So if I have a diode over here, we know that ideally a diode uh, operation, it looks like this. It has some sort of reverse saturation current. If I just consider that the reverse saturation current is very low, so let's say in the negative half, the response is 0 only, and over here you will get, if you increase the voltage, you will see that current will start increasing and then it will exponentially increase. Now, if I consider that my diode is a piecewise linear system, piecewise linear. So you'll see this is a non-linear system. What you do is basically you consider this you approximate this particular response by using a line. So what will happen is it would look like this, but still this is a non-linear system. Even though I am trying to make it linear by using some line-based approximation, but as far as system is being considered, we have seen that your response should be passing through origin only. Now here you can see that positive half is okay, but at the negative half, you can see there is a non-linear operation is there. So that is why the system is non-linear in nature. Now, can any one of you actually tell me that which of the activation function it basically resembles like this particular response? What sort of activation function we have read which has similar characteristics to this?
The ReLU.
Yes, so this is a ReLU. So this is a ReLU function, and this particular ReLU function, if you see any basic electrical engineering book and you see that piecewise linear model of diode, you will see that it basically resembles the same nature, the response, the transfer characteristics of the diode basically resembles the same structure as the ReLU operation. And as the diode is basically nonlinear operation, nonlinear device, therefore its characteristics is also nonlinear, and the same nonlinear operation that you basically read at in the deep learning section, and this particular structure is basically named as ReLU only. So all these things are interconnected with each other. So this is just for inference only. So what my basic aim was to show you that diode is a nonlinear device. Its characteristics, if we consider this is a piecewise linear model, though it will be non-linear only, and the ReLU function resembles like this particular operation only. So therefore, ReLU is also a non-linear activation function. So the operation that the ReLU comprise. So the operation, if I just write in terms of mathematics, it will be ReLU of x is basically max of 0 comma x. So therefore, this particular operation is a nonlinear operation. Same as if you see this sigmoid operation. So sigmoid is basically looks like this. So this is 0, and then it starts rising up. So the image is, yeah. So if I just remove this part, so at 0 you get 0.5 over here, and over here you get 1, and at the negative half you get 0. If the value goes down, so you will approximately reach to 0. So you can see again the response is nonlinear only, as because the response is not something like this. So therefore, this operator is also a nonlinear operator. So now sigmoid is nullified, rectified ReLU is also nullified. So what about the convolution function, whether this is a linear operator or not, and if it is linear, then why? Yes, anyone? Yeah, convolution function, is it a linear operation or non-linear operation?
Linear operation.
And how you can justify whether this is a linear operation or not? What is the justification? So for any sort of something like these particular questions, if linearity is being concerned, either you have to check whether the response is straight line passing through origin or not. This is one way. Otherwise, you have to check whether the system is obeying the superposition theorem or not. So these are the two conditions. So in case of convolution function, the convolution operation basically looks like, I will take inference from DSP only. So digital signal processing. So yn is basically h of n convolution with x of n. For example, if this is the block, this is the impulse response of the system, hn, unit impulse response over here. And if you provide an input of x of n, you get output y of n, then I can equate this as yn is equals to hn convolved with x of n. And if you know a little bit about DSP or any sort of signal system course, if you have seen, you will appreciate that convolution operation is a commutative operation. So I can write x of n convolved with h of n. If you want, I can prove it as well. Otherwise, I will just skip this part and consider that this particular relation holds true. Okay. So we need to check whether the superposition theorem is obeyed over here or not. So let us consider we have the system response as Hn in all three cases. And superposition theorem is basically states that you provide inputs, multiple inputs separately, you take the outputs, you do a summation of the output. Parallelly, you feed the linear combination of the input simultaneously, and then you check the output. If the output is same as the total output of the previous inputs that you have fed separately, then if they are equated, they are equal, then the superposition theorem is hold over there. Otherwise, superposition theorem is. So let us do the same. So let us consider we feed an input x1n and x2n separately, and we get the outputs y of y1 of n and y2 of n. So y1 of n, I can write it as x1n convolved with h of n, and y2n, I can write it as x2n convolved with h of n. Now what I will do is we have separately fed these two inputs over here. We got the outputs y1n and y2n. Now we'll take a sum. So let us consider y total, and at superscript let me write s, which will basically tell you that I have fed them separately. So y total will be y1 of n plus y2 of n. Now this will be x1n convolved with h of n plus x2n convolved with h of n. Now let me feed these two inputs simultaneously. That means x1n plus x2n. If I feed over here, and the output, let's say y naught of n. So y naught of n, I can write it as x1n plus x2n over here, convolution with h of n. Now if I just open this particular parenthesis, it will be x1n convolved with h of n plus x2n convolved with h of n over here. So I can see that y naught of n is equals to y total of n superscript s. So over here I can observe that when I feed when I feed the inputs together, and whatever output I get it over here, that is y naught of n, it is basically equal to the case when I feed the inputs separately and then I take the summation. So this basically states that superposition theorem is obeyed over here, that is superposition theorem obeyed. So therefore, if the superposition theorem is obeyed, so I can say that conv is a linear operator. So this is the main conclusion. Therefore, convolution function is a linear operation or linear operator, whatever you call it. Okay, so any query for this particular problem? I hope there is no query for this one. So let us move to the next question. So the next question states that which statement is true about deep autoencoders? So let us scan through the options. So option A states that they have single hidden layer for representing the latent space. So this is not true. You can have multiple number of hidden layers. That is why this is named as deep autoencoder. So in case of deep autoencoder, obviously you'll be having several number of encoder layers and decoder layers to encode this particular input representation. So over there, single hidden layer, it is incorrect. So option A is nullified. So second option is that they have few parameters compared to shallow autoencoder. So in the last class, I told you that if this is the structure of an autoencoder, So this is a single hidden layer based autoencoder. So you can see that this particular network architecture or this particular neural network is not deep. So these sort of neural networks are called shallow autoencoders. However, by deep, what we mean is basically you have several numbers of encoder layers, and let's say this one is your latent space, and then you have several numbers of decoder layers. So this is basically what you mean by a deep AE autoencoder. So you can see that as you increase the number of layers, the number of weight will increase. However, as over here the number of hidden layer is less, so number of weight will also less. So deep autoencoder, they have few parameters compared to shallow autoencoder. This is also false because we can see that in case of shallow autoencoder, the number of weights will be less. However, in case of deep autoencoder, number of weight will be much higher than what is there in case of shallow autoencoder. Okay, so option C is they excel at capturing complex relationships and features. So this would be off. Features of high dimensional data. So this is true because what you want using an autoencoder is basically you feed a high dimensional data as an input to this particular autoencoder, then you encode this whole thing into a lesser dimensional latent space, and then again you decode it back, and your main target is basically at the latent space you get a good representation information. So that is why this is true, because they excel at capturing complex relationships. So over here you basically extract the complex relationship and features. So we know that latent space is basically used to extract features from the high dimensional data. So that is written over here of the high dimensional data. So over there option C is the correct option. Okay, let us scan through option D as well. So they require supervised learning with labeled data. So autoencoder is an unsupervised learning. So therefore you don't need labels. You just need the data itself to train this particular autoencoder, because the loss function is basically MSE between X and X hat. So over here you can see that there is no need of label is required. So they require supervised learning with labeled data. That is completely false. You don't need labeled data to train an autoencoder. If you just have the data itself, you can train the autoencoder, as because autoencoder is basically comes under the unsupervised learning neural network. Okay. So next question is, which of the following is false about autoencoder? So autoencoder possesses generalization capabilities. Autoencoders. So this one is true. This one is correct, because in the last slide also we saw that autoencoder, what in option C, we see that they excel capturing complex representations of the high dimensional input data. That means they basically are able to generalize the type of hidden representation that is there in case of an input data. So they have the power of generalizability of the input data. So therefore, from the previous slide itself, from option C, the option A is analogous to that. So option A is true. Next is autoencoders are best suited for image captioning tasks. This is false, because autoencoders are generally used for anomaly detection, image segmentation, then feature extraction. But image captioning is something else. In case of image captioning, you need to have for example, you have a neural network over here, you feed an image, and at the output you need some captions. That means you need some words. So for that you need to have the label data in case of image captioning task. However, as autoencoder is an unsupervised learning, it does not require any label over there. So therefore option B is incorrect because this is false. In image captioning task, you don't need an autoencoder to train for this particular image captioning task over there. So option C is its objective is to minimize the reconstruction loss so that output is similar to input. We already have seen, because again, if I just write MSE between x and x hat, so that is basically the meaning that your reconstruction output should be as similar as the input. Option D is so this is true. This one first option is also true. Option D is false. And option D is it compresses the input into latent space representation and then reconstruct the output from it. So multiple times I have told you. So I think I don't have to again discuss this particular option. So this is also true. So option B is the correct answer. This is the false one. Okay. So if I go to the next question, the next question states that the Dirac delta function is dash at t equals to 0. So before that, let me ask you, how many of you have actually taken any DSP or signal system course? Yes, any one of you have taken any DSP or signal processing course in your undergrad?
Yes, sir, myself taking.
Okay. So okay, so at t equals to 0, so when you see t equals to 0, that means they are talking about the time domain signal, and specifically they are dealing with the continuous time signal. So in case of continuous time signal, you consider that x-axis or the time axis is a real valued axis. There is another convention is there that is called discrete time system, where the time axis is basically replaced by
N, sir.
n. So this is basically called sample, and this is integer. So previously it was real value. The t was containing real values over there, and in case of discrete system, you have n in place of t, and this n basically comprises the integer space. Now, for these two different notions, continuous time signal and discrete time signal, you have two delta functions. Both are called delta function only. So over here, this is delta t, and over here, this is delta n. But their definitions are somewhat this definition basically somewhat changes when you go from continuous domain to the discrete domain. So what is the definition of delta t in continuous time signals? Anyone? What is the definition? What is the functional definition of delta t or the property?
T is equal to 0, answer will be 1, sir.
Sorry,
Delta D equal to 1, T is equal to 0.
that
0
means
x.
it is 1 at t equal to 0
Yes, sir.
and 0 elsewhere.
0 T. Yes, sir.
So this is a mistake that most of the students basically do, this particular mistake. At t equal to 0, the value is not 1 in case of continuous time signal. So for that, we first have to see how delta function basically generated. Let's say you have a box function. I hope you guys know what is a box function or a gate function over here. So a gate function is basically, let's say, a unit area gate function you've been given. So the length is a and the height is 1 upon a. So area is equals to a into 1 upon a, that is 1. Now what you do, you reduce this width like this, like this. You keep on reducing this particular value. So if you reduce a, if a is reduced, then 1 upon a will increase. That means this particular width will be reduced and this height will go up. Now let us consider you reduce it to a very narrow extent. That means a value, let's say, tends to 0. Then what happens to this area value? So the area will still be 1. How? You need to take limit a tends to 0, a into 1 upon a. So this basically still give you 1. The area is 1. Now what about the height? Height is 1 upon a. So as a tends to 0, 1 upon a tends to infinite. So at t equals to 0, this delta function exists. That is true. So delta t exists at t equals to 0 only. Delta t is equals to 0 at t not equals to 0. At any value which is t not equal to 0, their delta t is 0. And the amplitude of delta t at t equal to 0 is 1 upon a. As a tends to 0, this 1 upon a value reaches to infinity. So that means at t equal to 0, delta t has value tending to infinite. So this is first property, this is second property, this is third property, and the fourth property is, if you sum over all the time axis, so minus infinite to infinite, delta t dt will be equal to 1. So this 1 is also justified because you do summation over here, everywhere the value is 0. Only at this particular area you need to calculate this integral value. Now this integral value is basically, integral means if you have been given any graph, integral is basically the area under the curve. Now the area under the curve is basically what we have evaluated over here. Area equals to limit a tends to 0, a into 1 upon a, which basically yields to 1. So that is why minus infinite to infinite, delta t dt is equals to 1. So these four properties basically a time domain delta function has. A time domain delta function is never equal to 1 at t equals to 0. That is a that this particular mistake does everyone. Every student I have seen, they do this particular mistake. These four properties you have in case of a time domain delta signal or the Dirac delta. So the question states that the Dirac delta function is dash when t equals to 0. That means the question is asking that at time t equals to 0, what is the value? So if you put a equals to that value is 1, so this one is incorrect. So the answer is infinity. So which we have already seen that the height is 1 upon a, as a tends to very narrow value or tending to 0. So therefore 1 by a will go to shoot up to infinity. So that is why delta Dirac is infinite when t equals to 0. So that is the main reason. So how many of you got this particular question correct? You can raise your hands. Okay. Okay. So this is basically the reason that why delta t is not 1 at t equals to 0. That is the main thing. But when you go to the discrete case, if you go to the discrete case, that basically we can write it as delta n. So there the definition is 1 at n equals to 0 and 0 at n not equals to 0. That means elsewhere it is 0 and at n equals to 0 there the amplitude is 1, and that is why this is called a unit impulse. Unit impulse function in discrete domain. Okay. Okay, the next question states that impulse response is the output of dash system due to impulse input applied at t equals to 0. So what is the correct answer for this one? And I need the justification. So first thing is, how many of you got this particular question correct? So can any one of you please tell me what is the approach that you have followed to get the answer, the justification? First, what is the answer and then justification? I can see two people have raised their hand. You can unmute yourself and just tell me what is the justification. Yes, any one of you can unmute yourself and tell me.
The answer is the linear and time invariant.
Yeah, and then what is the reason?
Uh, del of t is equal to 1, t is equal to 0. Based on the equation x of t is equal to y of t, x of t minus tau equal to y t minus tau. Based on the equation
Now,
For
any
impulse response,
reasoning apart from mathematics? What is
okay.
the intuition that you have applied? See, uh, over here in the question itself, the answer is hidden. You you have impulse response is the output of any system due to impulse input applied at t equals to 0. So you have a system over here which is characterized by, let's say, Hn, which is a impulse response, and you fed uh, again over here I'm considering digital signal processing. I'm not going into the analog signal based representation. So in many of the cases you will see that I will be using only the discrete time representations. So delta n that you have given, so delta n basically exists at time t equals to 0, or time t equals to 0. I can analogously say it that it is sample or n equals to 0 because both are analogous. Okay, so you fed a delta n over here, you get an impulse response. That means again you get an impulse only at the output, that is delta of n over here. Now what is the uh, meaning of time invariancy? Time invariancy means, for example, you feed a signal x of n, the system is characterized by h of n, the output is y of n. Time invariancy means if you delay the input x of n by alpha amount, then the output will also be delayed by same amount. That means x is delayed by alpha, y is also delayed by alpha over here. So that is basically meant by time invariant system. Okay, now time invariant system over here, let us see. You have given a delta which is existing at time t equals to 0 only. So you can see that you have given signal delta n over here, and you get the output which is also a delta n and which is also residing at n equals to 0. That means whenever you are giving a signal which is located at n equals to 0, your output is also starting from n equals to 0 only. That means you can see that you just put alpha equals to 0 in this particular relation, you will get x of n is equals to y of n. So this basically holds the relation of time invariant system. So that is why time invariancy, because you give an input which is starting from n equals to 0. If your system was not a time invariant system or time varying system, your output might be shifted by a leading phase or a lagging phase. However, you get the output which is also starting from n equals to 0, where the input was also starting from n equals to 0. So therefore you can see that the system is a time invariant system. Now, what about the linearity or non-linearity? So we can see that your output, let us consider this is output yn is equals to delta n, as they have said that impulse response is the output only. So yn is equals to, I can write h of n is, sorry, it is delta n. So if you feed delta n to any system which is characterized by its own impulse response, and you get delta n only. If you know again, if you know about the DSP concept or any signal system concept, you have seen the formula of convolution. That is, if you convolve delta n with delta n only, then you will get delta n at the output. So that means the impulse response that is sitting over here, it is basically giving you a convolution operation that basically leads you to getting the impulse response back over here. So that is why the system is a linear system. And time invariance, as because you can see your input is starting from n equals to 0, your output is also starting from n equals to 0, and you can basically verify it from this particular relation which is there in case of a time invariant system. So that is why this system is a time invariant system. If your system was being a time varying system, your output might be shifted by a lagging or a leading phase. What is that meaning? So for example, if you give delta n as an input, you might get a output which is added with a phase n plus alpha, or might be n, so n plus alpha would come over here. If this is the 0 line, then delta n minus alpha would come over here, and if this is the 0 line, delta n plus alpha would come over here. So you can see that your output is now shifted. Whether your input was starting from n equals to 0, now your output is shifted by something. So therefore you can see that it is not obeying this particular relation which basically a time invariant system has. So therefore you can consider that your system is a linear system and it's a time invariant system, because linear system gives you the flavor of convolution, which basically helps you to get back delta n from a delta n itself, and this is a time invariant system from this particular response. Okay. Okay, so this question is that you have an original image, you perturb this particular original image using some noise. So this is the noisy input, and this is the autoencoder output. So we can see that some sort of noise removal is happened. So this is a denoising autoencoder. So this thing we have also seen in our coding session as well. So we took a denoising autoencoder, convolutional denoising autoencoder in our code, Python implementation, and we saw that if I perturb the input images with some sort of noise, random noise, and if I feed this noisy data into the denoising autoencoder, at the output you get the denoised version. So the code is also given. You can just run it at your end as well. So option C is the correct one. This is the denoising autoencoder. Okay. So this is the last question. So the last question states that 10th question. Which application of deep autoencoder utilizes the extracted latent space representation? So the autoencoder, you have a latent space, you have a decoder. In many of the cases, in most of the cases, I should not say that many of the cases, in most of the cases, you'll see that decoder we chop off if we have to use the hidden representation or the latent representation, because decoder is just to train the autoencoder model. But our aim is not to get the reconstruction. Our aim is to get some hidden representation which is there in this high dimensional data, and the hidden representation will come at the latent space or the bottleneck space. And we chop off this particular decoder, and then we use this latent representation for our downstream task. It might be a classification task, it might be a regression task, and we need to scan through what sort of task we can use this particular hidden representations. So the first option is anomaly detection. So probably in this particular slide, in slide 7, I have already told that we use anomaly detection. We use them for anomaly detection, image segmentation, feature extraction. So already I have answered this one over here. So anomaly detection, it is true. Image segmentation. Also, I have told initially itself that for image segmentation also we use this autoencoder representation. And the pre-training of the other deep learning models. So already we have seen that pre-training of the deep learning models are there in case of, let's say, transfer learning mechanism, or you can check one of my paper as well. That is, you can go to Google Scholar and you can check this paper. So in this particular paper also we used a autoencoder which was pre-trained, and then we fed those representations into another deep learning network which was basically used for classification tasks. So that is why this particular option is also true, that pre-training of other deep learning models we can, for example, I used for MLPNN pre-training, and here they are saying that convolutional neural network, any sort of neural network you can use over there after the representations that you extract from the deep autoencoder architectures. So all of the options are correct. So option D is the final answer. Okay. So by this we have covered the week 7 quiz solution, and now let us head to the week 8 solution.
Sir,
So
I have
this
a
is
doubt
week 8.
on
Yeah.
previous slide, sir. Sir, here we use encoder also for the dimension reduction.
Yeah, we use encoder for the dimension reduction. If you use the undercomplete
Undercomplete.
autoencoder. Yeah, probably in week 12. So this is a 12-week course. Yes. So in week 11, you will see there is a autoencoder structure that is called variational autoencoder. There you will see you are not using a undercomplete autoencoder. So I am not going into that. When week 11 will come, you will automatically see what I am talking about. So till now, whatever problems or whatever solution or whatever things we are discussing, we are mainly considering that we are trying to reduce the dimension of the high dimensional data using a undercomplete autoencoder.
So means there they will say how to anomaly detection and like image segmentation.
For example, so for these things now I have to show you some hands-on. Okay, I can give you an example for anomaly detection. For example, uh, uh, you can train video anomaly detection. So you train a autoencoder. You train this autoencoder with normal events. Normal event means, let's say in a road there is no traffic rule violation is there, so that I am referring as normal event, and you try to reconstruct it back using this whole autoencoder architecture. Now your training set only comprise the normal events. Now let's say I give you an event. For this normal event, your reconstruction error will be very low, because you are training this whole model using normal data only. So your model is seeing the normal data. So, and you are trying to minimize the loss, that is MSE x comma x hat, and your x is basically only the normal data. So your autoencoder will try to optimize their weights and biases based on whatever data it is basically seeing, and you are feeding normal data only. Now at the test time, let us consider at the 1 second. Now at the test time, you 1 second. Just give me 1 second. A mail came. I have to respond. Yeah. So at the test time, you let's say feed a case where a person is riding a bike and he is doing some sort of traffic rule violation. Now, when you feed an abnormal event, so this is an abnormal event to this autoencoder. Now, at the autoencoder, your autoencoder model is basically has extracted very good features for the normal data. When you feed a abnormal data to your autoencoder at the latent space, it will not be able to extract good features over there. And it will try to use those features, whatever feature it extracts from the abnormal data, which is not good, and it will try to reconstruct it back again at the decoder side. And at the decoder side, as your representations or the hidden features are not good enough, you will not get a good reconstruction. Therefore, your MAC will become very high. Then you can understand, okay, what if I feed a data, abnormal data, and if I get a MAC value which is very high, that means the model has not seen those data in while training the model, and this is an anomaly case which the model has not seen yet. So by this way, you can do the anomaly detection. The main funda is that as you are training the model using normal data, your model is extracting very good features for the normal case, and it can reconstruct back very nicely those normal cases. Now, if you feed an abnormal data, your model is have not seen any abnormal data over there. In case of latent space, it will extract garbage features and it will try to reconstruct reconstruct it back using those garbage features. As those features are very bad, therefore the reconstruction will also be very bad, and therefore the loss will be very high. And then you can consider that if the loss is very high, that means that is an anomalous condition, that is not a normal case. So in this way, you can use a autoencoder for anomaly detection. You can search several papers at their video anomaly detection. You can get to know that the training mechanism is this particular one only.
Sir, one question.
Yes.
Yeah. So, sir, this anomaly detection will always be there, no, sir, because your training data and the validation data will always differ, right, in practical situations.
Yeah.
So this
so that is
anomaly will always be there in every model, like.
this is now this thing comes on that how you are training your model. If you want that, for example, anomaly detection means what? Your model has to understand when there is some sort of violation is there. If you consider, let's say koi mohalle ke chowk mein you put a CCTV camera over here, and that CCTV camera every time it is capturing, and let us consider mohalle ke chowk mein there will be no such, in most of the cases there will be no such traffic rule violation kind of things will be there, because normal people will go over there and they will probably walk through this particular road. And what happens is that as your model, as your training data, if the training data comprises only the normal signal, you are training the model using normal signals only. Now what happens is that let's say a vehicle comes and it does an hit on collision with this particular person. So then your CCTV camera will capture this image or video. It will feed to the model. Now this is an anomalous condition. Your latent representations will be bad. Reconstruction will be poor. Loss will be high. Then only you can understand that there is an anomaly. If you train with normal and abnormal with everything, then how you will understand that when anomaly is there or not? That is the goal. If you train with abnormal conditions as well, then the model is seeing the abnormal data as well. The loss function is still MSE of x comma x hat. Now for abnormal cases also, the loss will be very much less. Now at the test time, whenever a traffic rule violation is also happening over there, your model will also give very less loss value, as because it has seen those those particular images. So then how come you will do the anomaly detection?
So in a way that the system, the model with the high bias, high variance is actually the anomaly
You can
scenario.
say that yeah, you can say that some sort of high bias and high variance is there, because you are totally biased on the normal data only.
Exactly.
You are not seeing the abnormal data, so it is biased on the normal, and that is why you are getting high reconstruction error for the abnormal cases.
Got it, sir. Thanks.
Okay.
Sir, how can we get the I mean, for research we need some data. So video type or any
That you have to search. There are several universities are there. They collect the data, they make it public. There is our website is there. Let's say uh, if I type it over here, I don't know. You see, so this is a very big repository. You can get several types of data sets over here. You can search through this particular website. Otherwise, you can search through GitHub, Kaggle. Then if you are working on biomedical data specifically, there is a website called PhysioNet. So from website only you have to check. Otherwise, you can actually create your own data set. For example, at our institute, there are several groups where they are actually, even we are also, what we do, we collect the data by ourselves. We place some cameras in a daily basis. We capture images, capture videos, and we use those images and videos as our own training data. So we create data sets by ourselves also. So that could be one scenario. But that is something which is basically somewhat costly. If you have to buy something, high precision camera or something like that, or high resolution camera. But apart from that, if you want to use public data set, there are n number of repositories are there. You can use any of those repositories. In any IEEE paper, any standard standard IEEE papers, you can consider. You go to the dataset section. If you see that the dataset is public, they will give you the URL or any paper which basically refers to that particular dataset. You can download the dataset from their website itself. So for machine learning, at least for any area rather than biomedical signal processing, you will get several ample amount of data. In case of biomedical signal processing, you will see that there is scarcity of data is there in this area, in biomedical signal processing. Otherwise, in video anomaly detection, these are very old problems actually. So you can see several data sets are there. For example, what I can remember is one data set is there, Shanghai data set. So that basically deals with video anomaly detection. There are other data sets also, I cannot recall them, but Shanghai data set, it deals with video anomaly detection. Pedestrian data and some abnormality, something like bike passes through the road, even though the signal was red, some other anomalous events are also there. So you can check that particular data set.
Okay, sir. Thank you.
Okay. Okay, so moving to the week 8 quiz. So the first question is, your input image has converted into a matrix with a size. So the input image has size 256 cross 256 cross 3. This is 5. It looks like 8. And you have number of filters equal to 4. The kernel size is 7 cross 7. The stride is 2. Padding is 0. What will be the output shape? So this is your input, 256 cross 256 cross 3. This is the information that you have been given. K equal to 7 cross 7. Stride equals to 2, padding equals to 0, number of filters equals to 4. So we need to find what is the height, width, and what is the channel size, or C out. Your C in or channel in is 3. We need to find what is channel out, what is the height of the spatial dimension that we get out from this convolution, and the width. Okay, so for height and width, the equation we know. So that is basically output is equals to input minus kernel plus 2 into padding divided by stride plus 1. So here there is a catch. If I just use this particular formula, you will see minus k value is 7, padding is 0, so I can just omit this one. Stride is 2 plus 1, so 249 divided by 2 plus 1. So are we getting any whole number from this particular equation?
No, sir.
So generally we use this formula, but this formula is not complete. So for these such cases, when you do not get any whole number, so there the formula is you have to take the floor value. You can check any of the Keras, TensorFlow, PyTorch, any documentation. There you will see that this is the sort of equation that they follow. So over here it is 125.5, and sorry, so this will be floor only, so I have to be careful over there. So 125, so I need to reduce it down to the immediate integer value. So 125, so I have to take it down to the immediate integer, so it would be 125 only. So this is the formula that you have to follow. If you do not get any whole number out of this equation, then you have to consider the floor operation. Otherwise, you can just use this initial formula itself without using the floor operation. And if you get the some sort of decimal representation, then you have to consider that you need to follow the floor representation. You need to add this floor into the equation. Okay, so we got the height and width to be 125 cross 125. Now what will be the value of C out? How many number of channels you will get after the convolution? Anyone? Okay, so first you have to visualize the convolution operation for these sort of cases. What happens is you have a kernel of 7 by 7. So you put a kernel over here. So you can see the first anomaly over here is your input is 3-dimensional input. Your kernel is just a 2-dimensional kernel. So you can see that you cannot do the convolution operation because your input is 3-dimensional. Your kernel that you are convolving with, that is 2-dimensional. So first what happens is your kernel gets copied to the same dimension as the input. So from 7 by 7, you get a representation of 7 by 7 by 3. Then using the stride and padding and all, you do this whole convolution operation. You move it to the right hand side, then you go to the bottom, and then you scan over the whole image itself, and you get the first feature map. From the first, you have 4 number of filters, so this is from the first filter. Then the second filter, again a 7x7, a second filter comes to the picture. Again you have 2-dimensional data, 2-dimensional filter, but your input is 3-dimensional, so therefore your filter have to be copied to 3 dimension. Again it has to go traverse through the whole input data, and then it will give the second output. Then again the third filter will come, which is of 7x7 size. Again your input is 3-dimensional, your kernel is 2-dimensional, it has to copy it, and then it has to start the convolution, it has to go through all the pixel points in the input image, and then it will give you the third output. And the last one, it will come, if I just take this one, so again the last one will come, it will copy it to first to 3 dimension, then it will traverse through the whole input image, and then it will give you, it will do the convolution, and it will give you the final output. So you can see that you have 4 filters of size 7x7, which are now converted to 7x7x3, and then you do the convolution operation, and each time you get 4 different outputs. So that is why your output size will be 125 cross 125, and the channel will be 4. That means, if I just explain it easily, the number of filter is equal to C out. So if you see that filter number is 4, that means C out will be 4. And this is the interpretation. Every time you do the convolution operation, you get a feature map over here. So you have 4 different filters of size 7 by 7. So for all the 4 filters, you get the first output, you get the second output, you get the third one, and you get the fourth one. And this way, your output dimension is 125 cross 4. So option D is the correct option. Okay. So the next question states that you provide the raw input data over here, and these are sort of hidden representations 3, 2, and 1. We need to comment that what sort of representation, what level of representations that we get at 3, 2, and 1. So you can see that if you have a convolutional neural network like this is your input image. You feed with the CNN block. Let's say this is CNN1, this is CNN2, this is CNN3, and then you have a flattened layer. So this is flattened layer, and then you have the fully connected layer. And lastly, you have classification. Let's say you are doing 2-class classification, either 0th class or the class 1. So over here at the first stage, the lower layer, these are the lower layers. These are, let's say CNN3, this is the higher layer. So the lower layer learns low level representation. So by low level representation, what I mean is basically line, edge, boundary, etc. The high level feature, for example, for this particular case, this is a face recognition task. So for high level feature, what I mean is basically the higher convolution layer, whatever feature they learn, that are basically the high level feature, which could be like generating phase, and in between the higher and lower layer, these are the mid-level layer. So if I write over here, these are mid-level layers. So they learn mid-level representation, So by mid-level representation, what we mean is basically they basically try to learn the some patch representation. For example, eye, a nose, a lip, something like that. As far as this particular problem is concerned, for example, generating eye, nose, lip, ear, something like that. So now let us consider the let us see the images over here. So in third level, we can see that the third level is basically learning the line, edge, something like that. So over here, you can see that this is forming a boundary. These are learning the line. Over here also line. Here also you can see some sort of boundary is there. So this you can refer as low level feature. Low level. In option 1, in level 1, you can see that the model is now able to generate the faces, which is basically required for face recognition task. So you can see that this have to be a high level feature. This is high level feature. So by high level feature means we have already talked that this tries to generate the faces. So these are high level features. And as far as 2 is concerned, we can see that it is able to extract an eye. Over here you can see nose, something like that. Over here you can see lip, again nose, eyes. So these is you can refer as this is a mid-level feature. So now let's see that which of the option is correct. So level 3 is low level feature, it is okay. Level 2 is high level feature. So that is not, because level 2 we can see that it only expects eyes, nose, lips, etc. So this cannot be a high level feature. So option A is wrong. Level 1 is low level feature. So we can see that level 1 is a high level feature. So option B is also wrong. Let us see option C. Level 2 is low level feature. Again, it is wrong. So level 3 is low level feature, level 1 is high level feature, and level 2 is a mid level feature. So option D is the correct option. So any query for this one? Okay, so I hope no query is there. So the next question states that which of the following statement is false about ReLU. So we need to see which is false. Okay. So ReLU has an expression max 0, x. So this is true. Okay. So derivative of ReLU is 1 if x is greater than 0 and 0 otherwise. So the ReLU function looks like this. So the derivative, if I just draw, so this is ReLU of x, which is max of 0, x. So this is the direction of x. And if I do the derivative, let us consider this is y equals to ReLU. So if I do the dy by dx, and let's say this is the direction, so it would be 0 for the negative part and 1 for the positive part. So over here you can see that this is y equal to x only, and this is y equal to 0 only. So dy by dx will be 0 over here, and dy by dx will be 1 over here. So this is the representation of the derivative part. So this is also true. Okay. ReLU activation function was introduced in ResNet architecture. And implementation of ReLU has more computational cost than tanh and sigmoid. So ReLU, you have seen that either the value is straight away 0 or straight away 1. So the derivative is very simple. You do dy by dx, this will be 0. You do dy by dx over here, this will be 1. However, in case of sigmoid, let's say sigmoid of a or sigma of a, if you do derivative, that is sigma dash of x, what is the value? What is the function that we get if I take derivative of sigmoid? So we already did in several lectures that the derivative of sigmoid. So it is sigma of x into 1 minus sigma of x. So now if I just show you the complexity, it will be 1 plus uh, e power of minus x, 1 minus 1 e power of minus x, like this. So now you can see that if you are familiar with VLSI design, you might appreciate the fact that you need to store all these e to the power x values in some register, and then you need to do the computation. So for that, you can clearly comment that in case of sigmoid, the computational cost is very much high, because you need to again get the value of sigma x at that particular x, 1 minus sigma x. So therefore, in case of sigmoid, the computational complexity is very high. Rather over here, you know that for the positive half side, whatever may be the value is, whatever may be the value, you get 1 as the derivative output. And for the negative case, whatever may be the value is, you will get 0. However, in case of sigma of x, or in case of a tan of x, tan h of x, so tan h of x is just some manipulation over sigmoid function. So sigmoid was restricted from 0 to 1, and over here you get another f representation, but that is ranging from +1 to -1 over there. So in this particular case also, you do the this is a, you can do it as an homework, that what is the y equals to tan h of x, what is the dy by dx values. So there also you will see a humongous representation will be there for dy by dx, and you can see that again you have to calculate all the values of sigma and sigma of x, and this basically increases the computational cost. However, in case of ReLU, it is straight away either 1 or it is straight away either 0, depending on which side the data is lying, either on the positive half side or in the negative half side. So implementation of ReLU has more computational cost, that is false. So we have got that option C is the correct answer for this particular question. And whether it has been introduced in ResNet or not, as long as we got the option C, we got the answer. Frankly speaking, I don't remember all these kind of GK type of question, whether ReLU is introduced in ResNet paper or in VGG paper. These things nobody remembers all these things. For as you guys are doing the code, you might have to remember these things, but fairly as you get to know about deep learning, the nitty-gritty information nobody asks about. Okay. So the next question is, for a transfer learning task, which layer according to you more generally transferred to the task. So transfer learning is basically you have a very big model, so big NN trained on a very big data set, like ImageNet, and you have classification, 1,000 class classification over there in case of ImageNet. So 1,000 class classification. So in the previous in this particular slide, we have seen that the higher convolutional layer basically learns the high level representation. So high level representation means what? That it is now able to generate the faces. So that means these sort of information or the high level informations we do not require in case of transfer learning task, because we are trying to transfer the knowledge into some other database. So for those operations, for those transfer learning mechanisms, what we need is basically the low level information, or the information which basically comprises the information of line, edge, boundary, some sort of generalized information. So these generalized informations are held in the lower level of neural network rather than the higher level of neural network. Higher level neural network, they are basically high level feature, or more specifically they are task specific feature. What do I mean by task specific feature? You can see that your problem was to do a face recognition. Now you can see that at the higher end, the model is now able to construct the faces. That means it will help in face recognition. However, in the lower layer, you can see that you do not have any information regarding face. So that means this lower level feature you can basically transfer to any sort of transfer learning mechanism rather than transferring this higher level features, because those are task specific features. Your task may not be a face recognition task. Your task may be a regression task. So why do you need these high level features or the task specific features? So in case of transfer learning model, let me just show it like this. These are, let's say, low level feature layers, and these are high level feature layers. Please don't mind about the spelling mistakes. So these are high level feature layers. So you can transfer this low level feature layers, not the high level feature layers, for transfer learning tasks. So you can transfer this model over here. So this is the transferred layer. Then what you do, you initialize your own high level feature layer and do the classification on a very small data set like Pascal or like Iris. Even Iris you cannot do actually, because Iris just having some sort of vector representation. For example, Pascal only, or let's say Cipher 10 mini. So these sort of data sets you can use, or let's say any chest X-ray classification task. So you'll see many papers in IEEE. So where chest X-ray classification is done using transfer learning task. And you can check one of my paper as well, which is basically a YAMNet paper. So there we had used audio pre-trained model as fine tuning. So we basically, what we do, we basically transfer the lower dimensional layers, for the lower layers, not the higher layer. So we transfer the lower feature layer, not the higher feature layer. So for transfer learning task, which of the layer you need? It is basically the lower layers, not the task specific, not the higher layers. And often is you just can omit this one. Okay, probably I have copied this one 2 times. So I can delete this. Yep. Okay, so this question states that suppose you have image 3 channel RGB image means you have 3 channel image. So 256 cross 3 over here, and then what you have is filter of 100, kernel size is 5 cross 5, and you have to consider bias over there, and you need to find the total number of parameters. So how many of you got this particular question correct? And I need the answer. If you got this particular question correct, how did you proceed? I need the answer. Yeah, I can see one person has raised hand.
Answer is
Yeah,
D.
so how
Using
how
the
did you proceed?
formula
So what is the formula?
N into M into L plus 1 full bracket plus, sorry, into K.
But madam, how do you get those formulas? Because whenever you do, for example, if you've been given something, if I change the question in some other manner, the formula may get changed. So there could be a reasoning that how did you get to that particular formula. You've been given the solutions, you'll see that directly they have written those formulas. But what is the reasoning that you get that formula M into L into plus 1 into something like that? How did you get those
Sir, plus
what is the
1 means
intuition
with
behind?
bias. Yeah.
So let's say you have 10 number of filters. So how many bias will have? Let's say you have for this particular problem only, over here you have 100 such filters, number of filter is 100. So how many bias you will have?
Sir, only one bias.
One, sir.
No, so that is the reason that you need to see the you need to understand that how those formulas are coming. So let me first if I have the solution, let me see whether I have the solution or not. And if I have the solution, let me download the solution and let me show you that how they have calculated those values. But understanding is required over there. This is week 8, right? Solution. So it is like that 5 into 5 into 3 plus 1, and that is why you are saying that you have one bias, and then you multiply with 100. So here you need to understand why one has come, from where one has come, and whether one has any significance or not, or is it just a dummy value or a mathematical manipulation or something else. Because one is not for bias. It is actually for bias, but there is some mathematical manipulation is involved over here. You do not have single bias over there. Okay, so this is why you need to first visualize how this convolution operation is going on. So let's say you have this 256 by 256 by 3. The size is 256, 256 by 3. This is the input image. Now let's say you have a kernel of size 5 cross 5. This is a kernel of size 5 cross 5. So first tell me whether you can do a convolution with this single kernel only, with a single 2D kernel only. You have a 3D input, you have a 3D input, you have a 2D convolutional kernel. Can you do a convolutional operation over here? Yes, anyone? Already I have shown this operation in one of my previous slides.
No, sir. No, you cannot, because the image is 3-dimensional and the kernel is 2-dimensional. So the kernel has to be copied over all the 3 layers. Yeah.
Yes,
And then, yeah.
So it has to be copied first. So that means you can see you had a 5 by 5 kernel, but due to the convolutional constraint, as because you cannot do a convolution using a 2D data onto a 3D data, first you have to copy. So that means for a single, let's say you have 100 such filters, I am considering first filter. So for the first filter, you had 5 cross 5, but it has to first copy itself to a 3D data formation. Now you can see for a 5, it was 5 cross 5, but due to convolutional constraint, it has to be 5 cross 5 cross 3. Right? Now how many? Now you can perform the convolution operation. Fine. So 5 cross 3 for a single kernel. For a single kernel, you have this much of parameter. This is parameter. But this is for a single kernel. Now you have how many kernels? 100 such kernels. So for 100 such kernels, the number of weights will be how much? 5 cross, for 1 you have 5 cross 5 cross 3. For 100, how many will have? For 1 you have this much of parameter. So for 100 such kernel, how many parameters you will have?
Into 100.
Into 100. Okay. Now these are, as far as only weight is being concerned, weight value is concerned, the calculation is fine. Now they have said that you need to consider bias as well. Now for each of this convolutional kernel, you will have single bias. That means for one kernel, we'll have one bias. For 100 kernel, how many bias you'll have?
100.
100. It is like from this equation. So you have, let's say, y equal to wx plus b. For a single weight, you will have single bias. Let's say you have 3 such weights. So every time your equation will be what? Y equal to w1x plus b1, w2x plus b2, w3x plus b3, like that. So you have 3 such weight representations, so you have 3 such bias values along with this weight. So over here, you have one kernel. For that one kernel, you have one bias. So for 100 kernel, you will have 100 such bias. And we know that total parameter is equals to total weight plus total bias, right? So over here, total weight is how much that we have got over here. So if I just add one more page over here, so total weight is equals to total total weight plus total bias is equals to total parameters. So total weight is how much? You have got 5 cross 5 cross 3 into 100. And total bias, you have 100 kernel. For one kernel, you have one bias. For 100 kernel, you have 100 bias. Now you see 5 cross 3 plus 1. And then you get this 100. So this is how you get that formula. It is not that you have single bias. You have 100 such filters. You have 100 such filters. For those 100 filters, you have 100 bias. For 100 filters, you have 100 such weight. So this is the previous line that you have to first understand, from which you get this particular representation. So that formula that you are referring to, that comes from here. And if I construct the question in some other manner, you will see that directly if you use this particular formula, you will never get the answer correct. You have to go by this particular intuition, then only you will get the answer correct. If you directly follow the formula, you will make mistake. That is the main thing. You can do the mathematical operation and you can get the answer. Probably the answer is 7600, I think. Yeah, 7600. Yeah, any query for this thing?
Sir, can you repeat this 100 written as a one, the last two lines?
Yeah, sorry.
5 into 3 into 100 plus 100. Next line you written as 100 as a 1. Can you explain again, sir?
Yeah, I am. Yeah. Okay. So this line, have you got this line? How this line is coming? You got this point, or
Yes, sir, I got it. I got it. Based on the equation,
you got this?
yes, sir.
So let me just write it again. So what I'm doing, I'm just doing a mathematical manipulation over here. What I'm doing is, for example, you can see that 100 is common for both the cases, right? Let's say this is 5 cross 5 cross 5 cross 2 into a plus a. So I can take this a common. So I can write it as 5 cross 5 cross 3 plus 1. Can I write like this?
Yes, sir, yes, sir, I understood. Yeah.
So this A is 100.
100 value.
So this is how you get 7600.
Yes.
I think somebody is audio off.
Yeah, I think someone's mic is on, so you can turn it off.
Yeah.
Otherwise, let me mute the participant. Okay.
Sir, one more question. Sir, we consider
Yes.
we consider the bias for the filter. But what about there is also a bias in the model, right? So we have to consider
Oh no, that bias is something else. That bias is something else. That bias means you are actually, for example, you are praising the beauty of Taj Mahal. So So let's say you are praising Qutub Minar and there is Taj Mahal. So for someone who is living in Delhi, he will say that Taj Mahal is the most beautiful palace. However, if someone is someone who praises Qutub Minar, he will say no, that Qutub Minar is more beautiful than Taj Mahal. So you can for this particular inference, you can say that a CNN model is biased on Taj Mahal means that it has more inclination towards Taj Mahal. That means this is not the bias or the mathematical term. This bias means, for example, I am biased to someone. This is something like that. For example, if you have a data set, in biomedical case, again I am considering, you will let there is a data set, skin cancer data set. Skin cancer data set. In that particular data set, you have two cases. One is cancer, one is normal. Now, in case of cancer data set, they have only 100 samples. In case of normal, they have 5,000 samples. Now, if you train a model with this data set, you can see there is a huge imbalance. 50 times more data is there in case of normal signal, in case of normal class. What happens is that with this particular data set, the problem is that as the model basically sees most of the data is normal, it makes huge misclassification. It's most of the cases in the cancerous data are also predicted as normal only. In this particular case, you can say that the model is biased. The model has a bias towards predicting all the images to normal class. That means the model is biased to the normal signal, not the cancerous data. So this is basically meant by that bias. That bias means something else. That is, the model is inclined to some particular class. If you have 3-4 class and there is a, let's say, data imbalance, this problem is basically called data imbalance problem. You can search data imbalance and then you can see that skewness, model is skewed to a particular class, model is biased to a particular class. That bias refers to that thing, not the what you call the bias or mathematical term, something like that. Got my point?
Yes, sir. Yes, sir. Thank you. Yeah.
Sir, one more doubt.
Yes,
Suppose
yes.
without bias means the
Without bias, for example, mathematical bias you are talking about, right? Now I am getting confused. That means you are talking about this bias.
yes, sir. That will be zero
so,
value.
So then you don't have to consider this. Then this 100 will be out from the equation. You just have to consider this one, this term.
Okay, sir. Okay, thank you.
Okay. Yeah. Yes, so let's move to the next question. So the next question states that the statement 1 is adding more hidden layers will solve vanishing gradient problem to a 2-layer neural network. So this is pretty wrong statement, because let's say you have a model which has 2 layers, let's say 2 hidden layers and output layer. If you increase more number of layers, that means you are making the model more deep. Then obviously, while backpropagating the error, the vanishing gradient problem will come. The larger the number of layers or the deeper the model is, the problem of vanishing gradient will be more persistent. Because if you have seen the lecture itself, for example, this is F1, this is F2, and let's say you have also incorporated so many layers. Let's say you have incorporated 6 layers. So F3, F4, F5, F6, like this. And lastly, the output layer, and this is the input layer. Now you can consider whatever backpropagation rule you will do, output is equals to F1, F2, F3, F4, F5, F6 of the input. You feed an input, you pass through all these layers, then you get the output. Now you do the backpropagation. Let's say you need to calculate del O by del I. Now you can see that you have to pass through first this layer, sorry, from this part, from this side, from this layer, this layer to then the final thing. So you can see that for the layer, first you have to do the derivative del by, you need to do a chain rule. Then for the next layer, for this is chain rule 1, for the next layer, let's say 5, we'll have another chain rule, we'll have another chain rule. So this chain rule process will persist several times. And this chain rule, what will happen is that, for example, if you increase the number of layers, the multiplication will increase. And as well as what will happen is, for example, if you are using sigmoid activation, so sigmoid activation as a derivative is sigmoid of x, 1 minus sigmoid of x. Let's say you are in some point, you are getting sigma of x is 1/4. So you can see 1 minus 1/4, this multiplication will even further go down. So therefore, this is very dangerous. If you increase the number of layers, the vanishing gradient problem will still persist, and it will be very much prominent. And what will happen is that while doing the backpropagation using gradient descent tool, after few number of epochs, you will see that your learning mechanism has been stopped because the gradient has vanished almost 0. So if you use the formula, that is W of n plus 1 is equals to W of n minus eta into grad by W. So this will vanish. So this will be 0. So Wn plus 1 is equals to Wn. So which basically refers that your learning mechanism has stopped due to vanishing gradient. So statement 1 is true. Okay, statement 2 is making the network deeper will increase the chance of, sorry, what was there? Adding more hidden layers will solve vanishing gradient. So this is false because it will increase the vanishing gradient problem. Statement 2 is making the network deeper will increase the chance of vanishing gradient. So this one is true. So option B, statement 2 is correct. So last one, neither statement 1, 2 is incorrect. It is wrong. Vanishing gradient problem is independent of number of hidden layers. So this is crap. So this is also incorrect. So option B is the correct one because making the network deeper will increase the chance of vanishing gradient. The next question is, which of the following is false about CNN? So let us scan. Output should be flattened before feeding it to the fully connected layer. Yes, because the convolutional output, whatever you get, first you have to flatten it and then you need to feed it to the fully connected layer. So this one is true. Then there can be only one fully connected layer. This is also wrong. This is wrong. Because you have seen in my previous lecture that while doing the VNet architecture, we used 2 dense layers. So that means there is no hard and fast rule which basically states that there will be one fully connected layer. So this is wrong. You can use as much as fully connected layer that you want, but with the verge of you can increase the possibility of vanishing gradient. But there is no hard and fast rule that you have to apply only a single fully connected layer. So this is which is false. Okay. So option C is we can use as many convolutional layers in CNN. This is true because we can actually use as many convolutional layers. So you'll see that when ResNet came, it had probably 4 to 5 convolutional layer. Then VGG when came, it had 16 layers, out of which 13 were convolution layers. ResNet when came, ResNet 18, it had 18 convolutional layer, then many variants, ResNet 50, even ResNet 101. And even in later cases, you will see dense net. If you see the paper, so dense net 101. This is a huge, tremendous amount of parameters they have considered over there. So with the with the progress of Moore's law, that means in the VLSI domain, when the MVLSI, VLSI, these things have been significantly grown, so the computational power that at hand has been increased. So therefore, people have tried with different combination of or different sort of number of hidden layers into the deep learning network, and they actually increase the number of hidden layers in the neural network architecture. Okay. So this is a good example. So in this particular question, you have a 3D input of size 39 by 39. So this is a very good question. So 39 cross 39 cross 3. This is the input. So at the first convolution operation, the kernel size have been given 3 cross 3. Number of filter is 10. Stride is 1. Padding is 0. So first tell me what will be the size of the output for the first case. So it will be 39 minus 3 plus 2 into padding will be 0 divided by 1 stride plus 1. So it would be 37, right? So the output will be 37 cross 37. And what will be the channel size now, please? What will be the channel size? We have already discussed that how we can evaluate the channel size.
Filter, 10 filter.
Sorry? Please again, what will be the channel size?
Filter size. Based on filter size. 10.
Yeah, 10. Because number of filter that I have already told, number of filter will be the channel size or the output channel. Again, in the next case, you have 5 cross 5 filter size. Number of filter is 20, stride is 2. So over here, the 5 would be 37 minus 5 plus 2 into padding will be 0 divided by stride is 2 plus 1. So this will give you 32, 16 and then 17. It would be 17 cross 17. And what would be the number of channel now?
20.
20. Yeah, so it would be 20. In the third case, you have again 5 cross 5, number of filter is 40, and then you have stride 2. So it would be 17 minus 5 plus 0 divided by 2 plus 1. So it would be 12, 6, 1, so 7. So 7 cross 7. And what would be the channel size now?
40.
40.
Yeah, so it would be 40. So over here, we got the first convolution output, second convolution output, third convolution output. Now let us read the question. Layer 3 of the above is followed by a fully connected layer. So what we have seen in the previous slide, that output should be flattened before feeding to a fully connected layer. So this is a tensor. We have already talked about what is a tensor or a multi-dimensional array. You can see that if this was only 7 cross 7, we could have said that this is a matrix. Now we can see this is a 3-dimensional matrix, and we basically generalize its name as tensor or a multi-dimensional array. But this output, you cannot directly feed it to the fully connected layer. So what we have to do to feed it to the fully connected layer? What operation that we have to do before feeding it to the fully connected layer? Yeah, in the previous slide itself, we had discussed that output should be flattened before feeding it to the fully connected layer. So over here, we have to do the flattening operation. This flattening operation, did you guys actually run that particular LeNet code at your end? Have you run that LeNet code at your end? Or first, did you get the code or not?
Yes, sir. We got.
Yeah, so did you run that particular code at your end?
We studied.
Okay, so if you have studied, you can remember that there was a layer called flatten layer was there. Okay,
Yes, yes.
so a flatten layer was there. So flatten layer, what it does is basically it generates a 1D vector out of a tensor. So the 1D vector, the shape will be m cross n, m cross 1. So this will be a shape of a vector. And what will be the value of m? M value will be 7 cross 7 cross 40. So that means 49 cross 40. So it will be 36, structure 16. So 1 7. So that will be
1960.
yeah, sorry, 1960. So 1960. So the flattening layer output will be 1960 cross 1. So these you can feed it to the fully connected layer. If you have seen the LeNet code, you must have seen that there is a flattened layer. After that, we use the fully connected layer, or which is also known as dense layer. I request you all to check that particular code. So with theory, if you simultaneously do see the codings, then you can relate to these questions far better rather than just sticking to the theoretical part only. Because many of the cases, for example, these things, it will be helpful if you see, if you can relate to this statements when you do the hands-on practice. Because why only one fully connected layer? In many paper, you will see they have used one fully connected layer, but why only one fully connected layer? So then you will see that several other papers or several other GitHub code or other people use several number of fully connected layers. So from those things, you'll be able to answer these questions more efficiently rather than sticking to the theoretical part only. Okay, anyway. Okay, so for this question, is there any mistake is there in the answers, at least in the marking scheme? So let me first read it out. Consider a CNN which aims to classify images either rose, marigold, lily, and orchid. So it tries to classify to 4 different classes, right? So what sort of classification problem is this? We have seen in theory classes that there are two sort of classification tasks are there. One is binary classification, one is multi-class classification. So first tell me what sort of classification task is this one?
Multi-class classification.
It's a multi-class classification, yes. For multi-class classification, what activation function we use?
At the last layer, sigma.
Sorry, in the last layer, what activation?
Softmax.
Yeah, softmax. because softmax gives you the probability values for each of the classes. Probability of occurrence for each class, right? So that is what the last layer of CNN gives you a vector of logits. It is passed through a activation. So this activation is basically softmax activation. So did you tick to softmax activation or something else? Because I saw that in the website just today morning. I just saw they in the website they gave that leaky ReLU is the correct one.
Yes,
Is there any
softmax
anomaly?
not wrong.
Yes, sir. We
Sir, I ticked to softmax, but it got wrong.
It got wrong, right? But
for
if
me
you
also,
see
sir,
the
it's not
answer,
wrong.
yeah, but if you see the answer, so it is a problem for at their side. Uh, if you see the answer script that they have given over here, yeah. So they forget about the options. They have written that you can see softmax works best for the true class example because it gives you the class probability which sums to 1. So that means softmax is the answer, and which is ideal that softmax would be the answer because it's a multi-class classification problem. But probably there was some mistake, so they ticked A as the correct answer. So I might talk to them, and otherwise, what you can do in a mass, you can just put this query in the Q&A part or the ask question part or the forum, right? Then I will also talk to them because softmax is the correct answer, but they are writing leaky ReLU, so that has to be modified. Okay. So this is the last question of the week 8.
Sir, what will
Please?
be the difference between ReLU and leaky ReLU?
Yeah, okay, let me just go to the previous page. So ReLU, you have seen that ReLU for the negative half, you have this sort of representation. That means y equals to 0, and over here you have y equal to x. In case of leaky ReLU, in ReLU you consider that in ReLU you consider that your there is no contribution for the negative. There is no contribution for the negative side. Whatever value you get at the negative side, the output will be 0. That means negative side has no contribution. However, the positive side has contribution. As you can see that for every positive value, you will get an output. But in case of leaky ReLU, what people suggested is for the positive half side, obviously you will get some representation. But for negative side, instead of thinking that there is no contribution, let us think that there is some contribution is there. So this contribution is referred by hyperparameter alpha. So the equation will be y equal to alpha into x. So this alpha is a normalized value between 0 to 1. Right. So you can consider alpha equal to 0.3. So the slope will change to 0.3 and then you will get the corresponding values. So they have considered the equation like this. So this one was y equal to max 0, x. And over here they have two equations for the positive half side. So y is equals to x for x greater than 0 and y equal to alpha into x for x less than 0. So this is the equation.
Sir, I got.
So did you? Okay.
Yes,
Okay.
sir. Yeah, I understood. They will take the 0 side as considered as alpha x, whereas in the ReLU we take as 0 only. That's
Yes, yes, correct. So this is the last question, the 10th question. So the question is, imagine you are training a CNN For an autonomous driving vehicle to distinguish between pedestrian, bicycle, bike, car images. Okay. You have two options. Option one is a shallow CNN with just one convolution layer having 124 kernels and few fully connected layers. Second one is a deep CNN with four convolutional layers, 128 kernels in the first layer, 128 kernels in the second, 256 in third, 512 in fourth, and then fully connected layers. So if I just plot the argument over here, you have only one CNN layer for statement 1, and let's say you have two fully connected layers. And lastly, 4-class classification for 4 classes. Statement 2 is, and you have 124 filters. In case of statement 2, you have 4 CNN layers. And you have got some fully connected layers. Let us consider the number of fully connected layers in both the cases are same, as because they have not told both the cases, they told few fully connected layers. So let me consider they have same fully connected layers. And again, you have 4 different classes: pedestrian, car, something like that, whatever is there. Okay. And number of filters that they have given 128, 128, 128, 128, 256, and 512. If you sum up these things, 128, 128, you will get 124 only. Okay. So that is, they have written over here as well. Both option use the same total number of kernels as 124. Very fine. Choose the incorrect statement. So to choose the incorrect statement. So let us first talk about, can any one of you tell me that which of the model is more computationally complex?
Second one.
Sorry, which is having more computational complexity?
Second one, sir.
Second one, yes. So second one has high computational complexity, because you can see that it has 4 CNN layers. That means first it has to pass an image to this one, then it has to wait for the output, then it has to pass to the second layer, then it has to pass to the third, fourth, and then followed by that to the fully connected layers. However, in this particular case, you can see that you have an image over here, you just feed it to the first CNN layer, and you can followed by that you can proceed to the fully connected layer itself. So no such computational complexity is required, which is there in case of model 2. Okay. So another question, let me ask. For example, which of these cases actually able to extract wide variety of features? Either which of the models basically can extract wide variety of features? Is it model 1 or model 2?
Model 2, sir.
Yeah, model 2 can extract wide variety of features because you can see that it has 4 different CNN layers, so it can extract low level features, these can extract mid level features, these can extract high level features. Whereas over here you can see that only one CNN layer is there. So it will not be able to extract this wide regime of features which is there in case of model 2. Okay, now we can go to the options. Option 1 will give you higher inference speed since it can operate convolutions. First we need to choose the incorrect statement. Okay, so option 1 will give you higher inference speed since it can operate convolutions in parallel, whereas option 2 cannot be parallelized as results of next convolution layer is dependent on past layer. It is true. You can see that this would be fast because computational complexity is low. However, in option 2, in model 2, computational complexity is high. And here, for example, if you have to process the feature at this convolution layer, you have to wait for the previous output. So that means it is dependent on previous outputs. So you can see that in option 1 will have high inference speed. This is correct. And model 2 cannot be parallelized as the result of next convolution layer is dependent on past layer. So we have seen that over here, result of this layer is dependent on the past output. So option A is true. This is not this is correct. Option 2, deeper CNN with multiple layers can perform hierarchical feature extraction, thereby higher representation power and accuracy. So deeper CNN with multiple layers can perform hierarchical feature extraction. So over here we can see you have deeper CNN in case of model 2, and this deeper CNN can extract hierarchical features. That is, hierarchical feature means first you extract low level feature, then you extract mid level feature, then you extract high level feature. So there is a hierarchy is there. So you can extract hierarchical feature in case of a deeper CNN. So option 2 or the option B is also true, right? Now option C is option 1, shallow CNN with one convolution can extract 124 features from the image, thereby has higher representation power. It is false because you can see that shallow CNN has only a single CNN layer, and this particular CNN layer would not have very much good number of features because you do not have multiple hidden layers, it is not a deep CNN. It is not a deep CNN, and we know that deep CNN has the capability of getting better representation. So as because this is a shallow CNN and has only one convolution layer, so it does not have higher representation capability. So option C is false. And then option D is option 2 is a deeper CNN with multiple layers can extract more abstract features that depend on features of shallower layers and therefore higher representation power and capability. So this option D and option B, they are quite alike. So you can see deeper CNN with multiple layers can extract more abstract features. So they more abstract features by they are basically meaning this only, that it can extract an ample amount of feature from the CNN layers. So therefore, this is also true. So that means your incorrect option is option C. So option C is the correct answer for this. So any query? So if you have any query, then okay. I hope there is no further queries there. So we can end our lecture here, and probably in the next class, what I will do is I will take up that VGG16 implementation code. And for your reference, I have already uploaded the code beforehand. So if you go to the GitHub now, so let me show you. It is already uploaded there. So if you go to my GitHub account, so go to convnet. So I have created separate folder KNN, SPM, ConvNet, autoencoder. So in autoencoder, you will see normal autoencoder, denoising autoencoder, convolutional autoencoder, everything is there. And in ConvNet, so there are separate files are there. So this is VNet, VGG16 and ResNet 18. So let me just open VGG16 over here. So in case of VGG16, you can see that the whole code is given. You can just tap over here. You will be mounted to Google Colab, and then everything is given over here. You can just run at your end. I just ran for 5 epochs. So you can see that I just have ran for 5 epochs, and within 5 epochs, you can see that the accuracy reached to 98.93. But keep in mind that we are working on MNIST dataset. MNIST dataset is a very ideal dataset. This is not skewed to any particular class. However, in real life, in your research problem, you will see that you will come across several data sets which is basically skewed, which has data imbalance, and there achieving this high accuracy is very difficult. You need to do some sort of manipulation, some sort of loss function manipulation or initializer thing, or any sort of modification you have to do to get good results over there. So that is basically the main research problem there in real dataset problem. And I have done the testing as well. You can see that testing accuracy is 99.24. Within 5 epochs only you got around 100% accuracy. And you can see that the confusion matrix over here. And then you can see that what is the prediction result. So for example, this is the image, and true level is 7, you are predicting as 7. True is 2, and you are also predicting as 2. But you are doing some finite amount of mistake as well, because you are doing your classification accuracy is 99.24. That means you are doing some sort of mistake. Misclassification is there. So to visualize those misclassifications, I have also wrote a snippet that here you'll see that you can see this is true is 1, true level is 1, but the model is confused and it has predicted as 7. True
Sir,
is
can you
7, but
explain what is epoch?
what is epoch? Okay. Epoch is basically, for example, let's say you have a data set. Let me consider 216. Okay. You have a data set which has 216 number of samples, or let's say images. Okay. Now you have read that mini batch gradient descent, because mini batch gradient descent is better than both stochastic and full batch gradient descent. So let me consider the batch size as, let's say I will consider batch size is 6. So now what you are doing is you are actually segregating this whole data set into a bunch of, let's say you had initially in this particular bucket, you had a total of 216 number of images. Now what you have is, within this whole bucket, you are creating a batch of 6. So how many such buckets will be created? I need your help here. How many such will be there?
36.
Yeah.
36.
So 36 buckets. In 36 buckets, and in each bucket we'll have
6.
6 images. Now let us think that you have a CNN and you are using a batch of 6.
Oh.
So what will happen is that in it, let's say epoch 1. EPOCH epoch 1. 1 second. Just how Keras represents, let me just see, and then easy. Yeah. Slide. So when epoch 1 is progressing, what you'll do first, you'll feed this first batch, right? You feed the first batch, calculate the loss L1, then for this particular batch, you update the weight. In epoch, in same epoch, what you have to feed that into the CNN in each epoch. Now, let's say you are training the model for 6 epochs. 6 epochs. So in epoch, there is a thing is called iteration. In under epoch 1, iteration 1, what you will do, you will feed this first thing. Okay. Then you calculate the loss, update the weight. Then under iteration 1 itself, under epoch 1 itself, you come for iteration 2. In iteration 2, what you will do, you will feed this particular thing, this particular batch into the model, you calculate the loss, you back propagate it, weight update. Then again, iteration 3, you feed this particular batch, calculate the loss, weight update. Then how many times, how many number of iterations you have to do?
36.
36. So that means epoch 1 basically means that you have to perform 36 such iterations to feed this whole batch. Instead of feeding the whole batch at once, in case of stochastic gradient descent, what it will do, it will feed one image at a time. In case of mini batch, what it will do is that it will segregate that whole images, all images into small buckets or batches, and then within an epoch, there will be several number of iterations. For our case, it will be 36 such iterations will be there. So for 36 such iterations, you will feed these buckets, you calculate the loss, backpropagate it, weight update, go to the next iteration. And when you complete iteration 36, then only your epoch 1 is completed. Now again, you go for epoch 2. Then in epoch 2, again, you feed this image and do the same process. And when you will train in Keras, no, so you will see that when epoch 1 is going on, you will see that this equal to sign, this will see that you are progressing one by one, it will increase. Okay, so if I just exhausted my GPU limit, so you just run it at your end, you will see that there will be an arrow, and this arrow will progress with time. So you'll see that first you will have one single equal sign, then second, 2, 3, 4. That means the number of equal sign means the iteration under each epoch is progressing. So in your case, what will happen is that it will like this. You'll see that epoch 1, you will have 36 such. You have 36 such iterations, so it will be like this. When first iteration is done, so first equal to, then second equal to like this. So when the final 36 iteration is done, then you will see the total loss at 36 iteration, total accuracy, validation loss, and validation accuracy. And when epoch 1 is completed, then you go to epoch 2. Subsequently, you do all the iterations again. Then you go to epoch 3 and like this. So epoch 1 is this. Epoch means basically you have some bucket of data and you feed those bucket of data in each iteration under that particular epoch.
Sir, how many epoch we have to do?
It is also a hyperparameter. You have to plug and play with different values. For example, let me just give you an example. In this particular example, for example, this GitHub one, I ran it for 5 epochs. But if you see my papers, I generally run for 300 epochs, 400 epochs. But if you see somebody who basically works on NLP, they run for 10,000, 20,000 epochs. So you just cannot say that what is the ideal size of epoch that you have to follow. It is just the thing that you have to plug and play with.
Sir, if we increase the number of epoch, whether it gives more accuracy?
That is also a thing that I cannot comment about. There is a new phenomena is there, you can see that is called looking, probably I just cannot remember the looking. I saw this thing in LinkedIn probably in last 2-3 months. There is one paper has came, so they told that they had showed that if you train for prolonged time, they ran a CNN for 1 month. Now you can see, now you can think that if a CNN is running for 1 month, that means how many epochs they have considered. They ran it for 1 month, and then they saw that initially within 20 to 25 days, the accuracy was very poor. Suddenly, they saw a jump from 20% to 93%. So that is something called looking. So that came probably, I saw this post in LinkedIn probably 2 to 3 weeks back. So again, the thing is that I cannot comment that whether with the increase in the epoch, you will get substantial increase in accuracy. That is, these things you have to experiment with.
Thank you, sir.
Okay, so the codes are given, so you can run at your end as well. If you find any difficulty, you just post the question in the forum.
Yes, sir. Yes.
Okay, so I think we can stop.
Yes, sir. Thank you.
Thank you, sir.